So I'm the guy who has the honor of introducing our next speaker, Professor Leslie Gertsch, who is a senior research investigator and director of rock mechanics, associate professor of geological engineering, adjunct associate professor of mining engineering at Missouri S&T. There are sort of three motivations, as Carol said, for this workshop. One is fundamental science, one is planetary defense, and one is what are we going to do with these objects in a more industrial manner. Leslie's been thinking about this problem longer than anyone and has a lot of really good thoughts on it. I'm really excited about her presentation. So her research interests are obviously on extraterrestrial mining and excavation, rock mechanics, rock cutting. She's been looking at NEOs for, I think the first time we actually were in the same room together was at one of the space manufacturing conferences in the 1990s. So it is my real honor and pleasure to introduce Leslie Gertsch, and I'm excited to hear her remarks.
Okay, well, good morning, everyone. As they say in Monty Python, I'm now for something totally different. All right, this is just an outline of what I'll be talking about here today. A bit of a definition section, then a classification for asteroid mining, and then some unit operations for mining, stages in the life of a mine morphed to an asteroid mine, and then some potential mining methods, none of them strictly new, but something at least for discussion. First of all, mining is, as I think everyone knows, the extraction of geologic materials for human use. Mining engineering is applying science, engineering fundamentals, and the appropriate technology to recover those geologic materials. Now, you notice I haven't said what type of geologic materials. Generally here on Earth, we talk about solids, and we leave groundwater for the groundwater engineers, petroleum, oil and gas for the petroleum engineers, and so forth. But when you look at the details, there is a bit of overlap. There is some mining that is done with fluids in the underground. So that's why I've left it very general here. More mining terms. A mineral deposit is a naturally occurring concentration of a geologic material. You could say just a pre-occurring concentration. It doesn't mean that it's an ore body. Ore is anything that can be mined for a net benefit. Now, when I learned this, it was anything that can be mined for a profit, but that often gets frowns in some quarters. And when you look at it, sometimes you will see mining companies continuing to mine even when they're losing money, because there are other benefits besides profit. Long-term position in the market, for example. The ore, which can be mined, might include one target substance. It might include several. Sometimes they're mutually exclusive, depending on how they're processed. Most mineral deposits, though, are not ore, because either the concentrated material is not something we're interested in, and that's by far the majority of natural concentrations of geologic material we're not interested in because they're not materials that we use or we think we can use. The deposit may be too small to be economic, or the material may be in an unextractable form. The gangue is one term meaning the unwanted material. I tend to call it waste. That's intermixed with the target substance. So what we're ultimately interested in doing is separating the two. We want the target substance. We don't want anything else. The less we have to handle anything else, the better off we are. Reserves versus resources. These terms are often mixed up, but they actually do have legal definitions, and I'm not really giving those to you here, but just the sense of them. Reserves are ore that is known to exist and is currently available and economic to mine right now. Resources are potential ore, so reserves are a subset of resources, not the other way around. Right now, we don't have any measurable resources or reserves anywhere. We do have some very vague resources we think are out there. Theoretically, they're out there, but we haven't got measurements on them. Measurements and the quality of the measurements for calculating tonnage and grade, basically concentration and amounts, are crucial for reserves. Recovery, it's something that we won't really be talking about much here, but it's worth remembering. It's the proportion of the in-place target material. In other words, the proportion of the substance of interest, the ore, that cannot be separated from the waste material, or the proportion that can be separated. I have a that's supposed to be can be separated. That's the recovery. And the dilution is the amount of waste material that is bound to the target substance that you cannot separate from it. So you can never recover 100% of what's theoretically there. And you can, you always have a little bit of material that you don't want when you're processing it. You cannot escape that. Some recoveries go from 20% all the way up to 95%, depending on the material that you're recovering and the circumstances of the mineral deposit. Small body classification for mining. Now, this was put together about 20 years ago with some colleagues, and we've started modifying it a little bit. I'm going actually back to the original classification because the modifications aren't as pertinent here and we don't have a whole lot of time. Now, these are applying to all asteroids and comets, not just necessarily the near-Earth objects. This is very, as you can see, there's some relationship with the spectral classifications, but not necessarily one-to-one. And we're interested in how these materials behave when we fool with them. If we hit a few of them together, or if we do some drilling and blasting very precise, what can we expect to happen? Group 0 is the ice composites. They can be very weak. Of course, we're judging this on most of our terrestrial experience with, of course, some laboratory and theoretical work. They're mostly ices. Basically volatile ices with or without organic compounds and with varying amounts of refractory materials. Group 1 is friable rock, and that's not necessarily the next step up in strength or resistance to fragmentation. It's very similar to Group 0. In fact, it may consist in some measure of extinct comet nuclei, perhaps. Possibly some others as well. There's been talk recently about fairy castle textures. Those would probably fall in Group 1. Low volatile amounts, quite weak, possibly weaker than some of the ice composites. It depends on the composite sizes and aspect ratios, their shapes. Group 2 is the hard rock, and that's what most of us think about when we talk about mining. We think of Western hard rock mining where you dig tunnels and you put off blasts and it's all very sharp and hard. We're very confident when we talk about fragmenting those, but in space we've got a little different environment, so there may be some differences we don't expect. In fact, that may be the category we have the most trouble with because we think we know it better than perhaps we do when we get out there. Strong, very brittle, most similar, as I said, to what we've done before. Metallics, Group 3. There's the massive metals, maybe ductile, but again, we're thinking largely about our terrestrial experience. And as you increase the amount of silicate minerals, silicate rock, then we have the importance of textures. How interfingered are the metals and the rock? And that's going to greatly affect how we can separate the two. It depends also on what we're looking for. What do we want to mine? Now, these are just some potential examples of these categories. These are, as I said, potential, notional almost. Obviously, Comet Churyumov-Gerasimenko is a very likely member of Group 0, but no, it looks like we've got some interesting morphology here. And what does that mean in terms of extracting what we want? That's what we're looking for. How do we extract what we want with the least effort and the least dealing with stuff we don't want? Group 1 example, perhaps Mathilde, with its high porosity, is an example of that. Group 2, perhaps Ida. Of course, it's got a nice layer of regolith on it, so it's the distinction between what's in the regolith and what's beneath. There is going to be a continuum, I'm sure, but it's still early days so far as the mining perspective is concerned. Group 3B, Lutetia might be an example of that, a mixture of metals and rock. to certain, whatever the texture is, can't really tell at this point. Now I'm going to shift focus just a little bit here and talk about the unit operations of mining. And those are the generic fundamental activities that you need to do to acquire the ore while minimizing the handling of the waste. Now here on Earth, there are basically, we start with fragmentation. That's where you're detaching the ore from the surrounding rock mass. The excavation is when you're removing the ore from the surrounding rock mass, and often these two are combined. Transportation, we move the ore through the process from where we've found it, which is where the initial fragmentation, the primary fragmentation, has to take place. The excavation, another way of thinking of excavation is picking it up. So you break it off and you pick it up. Then you move it to where you can do the rest of your work with it, which might be right there at the face, the working face. Or it might be miles away, and that happens sometimes. Beneficiation, that is increasing the concentration of the target substance. We're actually now breaking the material down to whatever form it needs to be in, where it can be most readily separated from the waste material. And then throughout all of these, we actually have support activities like in any industrial process. You need to make sure that the equipment is working properly, that you get the supplies you need, that you take away your product and get it sold, all that sort of thing. These are the unit operations. Again, the way they're broken down here is very terrestrially biased. But at the same time, we have to remember what we're trying to do with this. And the bias comes about from the fundamental constraints of where this is happening. Here on Earth, we've got a unidirectional, constant magnitude gravity vector. Down is down. Very few of us have ever known anything very different. There is, relatively speaking, an energy scarcity, but a mass abundance. Generally, mining equipment, as I'm sure you've noticed, is very robust, very brawny looking, because especially the stuff that breaks the rocks, has to deal with the maximum forces and not the average. You know, it's got to be able to do that. And the easiest way to do that when you don't know quite what you're going to run into, because you never know what you've got, so you've already got it, and it's over and done with anyway. You never know what you're going to run into, so you have to prepare ahead of time. You don't want to break your machines very often because they can be hard to fix. So obviously you want robust, flexible machines that are easy to fix. Well, those things don't always go together very well with different machines. So we tend to overdo on the math a little bit to give us that added cushion for things we don't expect. For asteroids, we're going to have a variable gravity vector. It's very light, very low magnitude, but a variable direction as well. Just looking at some of these odd-shaped bodies and looking at their gravity gradients, it looks like a hill is not necessarily, gravitationally speaking, a hill. So it's going to be very different in this regard, and we rely on this quite a lot. Energy abundant, at least potential abundance. We have launch mass limits, which is not quite the same as the mass abundance we have on Earth. Of course, we do fight with that sometimes on Earth, but not quite to this extent. We have some other differences. Sometimes it's difficult to access the deposit because we have a very large planet, and even the largest mineral deposit is a very tiny, very small part of that volume. In fact, it's a very small part of the upper crust volume. So we can access usually something near one side of it, the top, whether it outcrops or not, but accessing the sides and especially the bottom is very difficult. With asteroids, we have a difficult location access, but we also have the ability that we've got a much greater surface to volume ratio. And that is going to be an advantage, I think, that in the long run will be very groundbreaking, so to speak. Sorry. The terrestrials, all our mining processes, even now, even the highly automated ones, even the the bulk mining methods were originally derived from human physical capabilities. We went out, we found rocks in streams, we broke rocks with our own tools. And even now, there are types of mining that are mostly possible only because people get in there and do it themselves. And even the most advanced ones actually come from that. If we can actually take people out of the loop, we actually will have some very different types of mining that may not look anything like what we have so far. And some of us have been thinking about what that would be here on Earth, and it's very difficult to do because of the ingrained culture. But I think when we get out into space, we've got much more of a possibility of looking at the basics of getting what we want without messing with the rest, and we can do things we'd never even think of on Earth because we can't get out there and dig a hole with a shovel. Here on Earth, we tend to want to do that. When something doesn't work well, we'll go get out and do it on ourselves. We can't do that in space. So it's going to force us to think outside the box, which I'm sure you all know anyway. Okay, just some brief examples here of some of the variety of mining methods already here on Earth with that first set of constraints. Here we've got a small sand and gravel pit. Our first 3 unit operations, transportation, excavation, and some of the transportation, or fragmentation, excavation, some of the transportation is accomplished by track hose. We've got 2 of them here. We've got one here that's loading the size separation system. We've got one over here. This is actually a fairly unusual way of doing this because track hose are not good for transportation. They don't carry very much and they don't go very far very fast. Further, the beneficiation is by the size separation, this orange device here, and that's a pretty simple one too. Further transport, as you can see in the foreground, is by truck. Site maintenance is by the bulldozer, basically site cleanup and such. You have to make sure that your roads aren't going to be wearing down your tires too much. Actually, truck tires are one of the bigger costs in surface mines. Even sand and gravel pits like this alluvial pit. Alluvial, basically river gravels, river sand. So, and that actually brings me to another point I'd like to make, is that we try very hard to take advantage of all the natural processes that are occurring. That's why sand and gravel is often, when possible, mined from alluvial river type gravels, because the river has already done some sorting for us. It's put things in one location so we can get to them instead of having to go up in the hills and scrape up all the pieces that are being weathered off of the mountains. The river has very conveniently gathered them all and put them in a central location. That's the trick of being a mining engineer, actually an exploration geologist really, is to find where nature's processes have already done part of what you need to do. And that's something to keep in mind out in space as well as here as on Earth. Another example, a large open pit gold mine, which is more what a lot of people think of. Here we've got fragmentation by drilling and blasting, excavation by the hydraulic excavator here in the center, and transportation by these big off-road haul trucks. Liberation is by crushing and grinding, and what that does, it breaks these quite large pieces. I suppose I should use one of these things. These quite large pieces into particles that are just the right size so that most of them are either or waste. You don't want a particle that is part ore and part waste, because you're going to have to decide, does it go into the mill to be processed or does it go to the waste rock pile? You have to make that decision. And crushing and grinding is designed to get just to that size, just a little below that liberation limit, but no lower, because grinding is the most energy intensive part of any mining process. If you have to grind, your energy costs go way, way, way up. Separation of the particles, in this case, since it's gold, is by carbon adsorption and cyanide leaching. but for different ores, it would be some different process. It depends on the surface properties, sometimes the body force properties. Whatever property can distinguish the ore from the waste will be put to use, often in sequence, in multiple steps. It's not very often that you have only a single step that will do all of the separation that you want. Here's an example that's an underground copper mine. As you can see, one of the mine openings there over on the right. Fragmentation is by drilling and blasting again. Excavation is by a load haul dump machine, which is just an underground version of a front end loader. You know, it's just lower height. And haulage is by truck, again lower height. It's a little bit difficult. It's hard to take pictures of these things underground. This is not my picture, but it is. Anyway, we've got some ventilation ducts up here. You can see the rock and some of the ground control devices here. That actually is wire netting. And some, well, actually it looks more like, we've also got some, it's an older mine. It looks like we've got some water pipe. Separation or liberation again is by crushing and grinding. Oh yes, transportation. It starts out with truck, but elsewhere in the mine there's belt conveyors, and then there's also a hoist. Actually, usually several hoists in these underground mines. So moving it doesn't necessarily mean you've got one way of transportation. There's lots of them. Which is the most effective for what you need. And separation is by froth flotation, of which we've got a picture here. Again, these are surface properties, chemical surface properties that are taken advantage of. Sometimes you float off the ore, leave the waste behind. Other times you float off the waste and leave the ore behind. Depends on the chemistry, which depends on the mineralogy, and not just of the ore, but of the waste as well. Here is an underground salt mine where nobody's underground. This is liberation. You notice we're going straight to liberation. We're not doing fragmenting, although you could. Sometimes for other other materials they do. We're just going straight to chemical dissolution. And transport is by the slurry pipeline. Concentration is by evaporative precipitation. So you don't have to necessarily have big trucks and drilling and blasting to do mining. In fact, there are some segments of industries that I consider mining who very vehemently do not wish to be called miners because of political and environmental problems that have been created in the past, and unfortunately probably a few even nowadays. And we'll talk a little bit more about that as we get to the stages in the life of an asteroid mine. Now this is taken partly from a road mapping exercise that NASA did about 10 years ago for ISRU, the in situ resource utilization aspect. I think that's one of the less successful names, but oh well, it's what they call it. It starts out for the ISRU part, resource assessment. What do you have? Where is it? What's it like? Resource acquisition, beneficiation, and then site management, which is not sequential. It actually is part of the other three, but it's important enough to call out separately. The assessment consists of the prospecting, the exploration, and the development. Prospecting is just looking to see what you've got out there. Exploration, you've got a few targets, you're winnowing those down to the most likely. Development is preparing your selected target for the acquisition part. You're developing the site for mining. Now, resource acquisition, this chart right now is set up for mining anywhere in the solar system, which includes atmospheric gases. Obviously, we don't expect that for asteroids. We do expect subsurface fluids, which could be gases. I don't think liquids necessarily. But once we start, for example, I'll give an example in a minute about heating a volatile-rich asteroid, we're going to be having gases that we're going to have to deal with. So that is going to be part of it. We're going to have to worry about possibly mining regolith. Our ore fraction may be in the regolith. It may be in the rock beneath the regolith. It may be in both together. Which is easier to extract from, which has what you need. It also might be in openings as product. Instead of the raw material that we're producing, perhaps we're producing a space underground where we're protected somewhat from the environment of space. So it's not just the solids that might be the product, the openings might be as well. This would tend to be for larger bodies that are somewhat competent, cohesive. And also waste materials. The fuel left over in the tanks that is too small to actually go through the pipes and actually work is something that could be useful for something else. So even though it's not strictly speaking a natural geologic material, it is a target for mining. Resource beneficiation can be accomplished, first of all, as I was talking about, making the pieces small enough so that each one is either ore or waste. You can also do that with phase change. It doesn't have to be solid. You can change the solids to liquids, gases, vice versa, whatever gives you the most effective separation mechanism that you can do. So these two are going to depend on what you're after. Separation then, of course, depends on what you're after. Separation of gases is different from separation of solids, et cetera. So there's a lot of stuff hidden in these categories. And then, of course, materials handling, which is part of all of this. And it's actually part of site management as well, although we call it transportation and storage here. These are all of the support aspects. I don't think I want to go into them in great and glory detail, but site planning is what you're starting with. These are in roughly chronological order, although they overlap a lot. Closure and reclamation. It's not something people think of when we talk about asteroid mining, but it will be fairly important because the idea of reclamation is to prevent future problems. And I'm actually going to go into a little more detail here. All right, prospecting. We need to decide on a target substance. You don't want to go out there and say, oh, I just want to mine everything. That would be impossible to make a business case for. You have to know technically what you're mining. What is your target? Once you've decided that, then you can locate some target NEOs, or bodies. Actually, any asteroid is what this will apply to, but this is a nod to the fact that in this morning we're talking about near-Earth objects. The exploration is to gain access to that near-Earth object and to characterize it. And just in a very general way, we want to know its surface properties, we want to know its internal properties, and its orbital properties, all with a focus on mining. There's a very great overlap and coincidence with what we need to know for science. But we need to know them for different reasons. So perhaps the precision with which we need to know a certain thing might be different. And that needs to be kept in mind. To prepare the NEO, this is development. We're going to need to figure out how to anchor things to it, possibly. Not each of these is necessarily going to be the case for everybody that we're going to mine. We might need to anchor it, tether things to it, and maybe not. We might need to, almost certainly we're going to have to control its motion. We may have to despin it. We might want to spin it faster. We are probably going to need to restrain it. We don't want uncontrolled catastrophic fragmentation. We want controlled fragmentation. We're probably going to have to install operations platforms of some sort. We're going to need to bag all or part of it, maybe, depending on our, how we're going to be looking at it, or what target we're looking at. We're going to need to install support equipment of various kinds, again, depending on the mining method. We've already talked pretty much about the mining operations. We need to access the ore and we need to remove it. Beneficiation, we've got the liberation part, the separation part. Transport, which includes supplies and support. Mining, during mining we're going to have transport. And it's not necessarily things that we have to carry back and forth. There's going to be a fairly major component of ballistic transport. Make sure these particles from that particular shot are going in the proper direction. We don't want a fog of fines around our asteroid. That would cause lots of hazards. Processing, transport, marketing, transport, closure and reclamation. Obviously, we need to remove and recycle our equipment. And we need to, most of all, prevent future problems. And that covers a huge range of things. Some potential mining methods. Now, mining method is how the unit operations are accomplished for a given deposit type. because the same unit operations, as I've already shown, can be accomplished by lots of different technologies, from the complex to the really simple. They need to take advantage of the environment and also advantage of the ore body characteristics. Now, I've given some terrestrial examples that I think I'm going to skip over in the interest of time, but these are just a few from the many thousand years of history, just mainly in the past couple hundred. These are some possible mining methods that we could apply to, in this case, if our target is volatiles ices. This mining method is derived from in situ solution mining and also block caving. Likely asteroids will be the group zeros. The mining sequence, probably, these are for the bigger bodies, and we've got, these are the sort of poster children, I suppose you could say. We're going to probably not, for the bigger ones, we're going to have to fragment it into something we can fit into a bag. And some of our bags might be large, but the smaller ones we could probably just put entirely in a bag. Heat it through solar mirrors, some sort of solar concentration mechanism to drive off the volatiles. And of course, the thing is, you're still going to have to refine those and purify them, because you're going to have a mixture of things. You've got different volatiles obviously coming off at different temperatures, but there's going to be some process controls that are going to have to be worked out. Fragmentation of the refractory portions that are left behind, they may self-fragment, in which case you might have a real problem on your hands. Or you may have to go in and do a little bit of selective shooting blasting to fragment them in a controlled way, and repeat this as needed. For rare earth elements, and these I'm just sort of pulling things out of the air here. This is a mining method derived from bulk mining of disseminated metal ore bodies like copper and some gold. Possible asteroids might be in any one of groups 1, 2, or 3. This is something called spin caving, where you would maintain or possibly increase the spin, set up a couple of opposing bags open on the opposite sides of the body, and then blast off the layers into the bags, and you're just keeping this whole thing spinning the whole time. And then basically, when you've got the whole thing fragmented, you pull up the bags and let them go a few times and get things to sort themselves out. Some interesting research could go on there. Platinum group elements. In this case, this is a mining method derived from narrow vein deposit mining methods. Probably cohesive group 2 bodies, large ones. You locate the vein outcrops, you fragment and excavate them with gripper-based continuous mining machine. This is actually an axial type road header or boom header. They've got various names. And of course, it would have to be gripping the walls of its tunnel. And potential smelting. Lots of people have thought about this one. We're probably going to want to bag the body, but there's a lot of detail I've kind of left out here, but you can see many other people have thought about it. And what about rubble piles? It depends on the particle compositions and their sizes, and their size distributions too. I propose that we would like to gain experience with the small monolithic bodies, and because the mineral economics will be determining the minimum size, and the orbital dynamics and the rock strength, the body strength I should say, will determine the maximum size. Then we can move up to multi-component bodies. Now, this is from a relatively recent paper that seems to indicate that of Itokawa, we've got a fairly more dense. This is 2,850 kilograms per cubic meter against a more of a rock particle or fragment, 1,750 grams or kilograms per cubic meter density. Mining method with respect to size. Basically, we might have to use a hierarchical approach, and that's actually done now in some of the larger terrestrial mines. And there we go. I'm a bit over, sorry about that, but do you have any questions?